energy, it's amazing that we've taken so long to talk about energy. It's one of the fundamental ideas in physics, and in fact, it can be a little bit difficult to understand after learning a lot of vectors. As mentioned with work, it's a scalar quantity. Its unit is a joule, just like work. And in fact, sometimes work and energy actually intermingle so much that people get confused about the differences between the two. I'm going to just talk about the various forms of energy that you can have, and just show you a little bit of the breakdown of how they arrived at these. Kinetic energy is a half mv squared. Realize here that this v is speed. Okay, that's speed. Make sure you're aware of that. It's not velocity. Again, this is all scalar. Notice the squared part of it. In other words, the faster and faster you move, it actually has more and more energy because of that. It's the reason that if an asteroid did come hurtling into the planet, could destroy it. The reason being is because it would release so much energy. They always talk about, so many atomic bombs worth of energy from a single asteroid, not because of its sheer size, but because of how fast it's moving. And that energy has to turn into something, and it'll probably turn into thermal energy when it hits our planet and heat it up very rapidly, and also cause a lot of other effects. Where does this potential energy come from? Well, mgh, you'll realize that the reason we have this is because suppose I have an object at above the surface of the Earth at some height h. The work that gravity would do, if I just dropped it, well, gravity would equal force times gravity. Okay, gravity would pull down with Fg, which is equal to mg. Well, it's going to be a force times gravity over a certain distance. And remember that force times distance is your work done. In fact, this is really just force and distance. Okay, and that's really just force and distance, which means the potential energy actually will be the work done by gravity after I let it go. What does this work turn into? Well, you'll find out right away. It's going to turn into kinetic energy. And we can find out how fast things are moving at a new way beyond kinematics. Potential energy of a spring, again, it's half kx squared. Where do they get this from? Well, this actually is, I'll give you a simple explanation of it. If you think of the formula for Hooke's law, and it was F is equal to kx, okay, there's the force. Well, it turns out that if a spring acts, let's say I have an object here, here's a spring, and there's some mass attached to it. If I pull this mass out and let it go, that average spring will be changing as it moves. Now, we want to take an average of it, so what do? We take the average by saying, well, let's just figure out what half kx is. Okay, that's like the average force over that entire time. Okay, and it'll go to 0, but at the beginning it'll be the most. And we'll just say half kx would be the average as it goes back to equilibrium. Well, if you take that and you multiply that by the distance that it moves, and the distance that it moves to equilibrium would be, you guessed it, x, which if we multiplied work equals force times distance, you have the force times another x, and lo and behold, you get this, the potential energy of a spring. Okay, very, very, very useful quantities. We'll look more at these, but just in terms of plugging them in terms of converting this, you'll realize that this potential can go into kinetic. If I let this object go, it can turn into kinetic. It can also go into potential and vice versa. These are the big three that we're going to look at. A very important theorem is called the kinetic energy theorem, and basically the net work done on any object can result in a change in kinetic energy. How does this look? Well, let me first of all just remind you of this important law, F equals ma. Okay, F equals ma. Well, instead of writing A, what I'm going to do is I'm going to rearrange this in terms of a known kinematic equation. The known kinematic equation is Vf squared equals Vi squared plus 2AD. I'm going to rearrange this for A, and I'm going to write that as Vf squared minus Vi squared divided by 2D. I'm going to plug this all in here and just say, well, then that net force is equal to m times Vf squared minus Vi squared divided by 2D. Why am I doing this? Well, I want to change this now and say, well, this is going to be my force, and my distance, okay, if I multiply it by my distance, that would give me my work. So in other words, if I took this quantity and said, well, instead I want to find out what the net work done on something is. That's going to be equal to net force, and I have to kind of slip this in here, times d. Okay, so it'll actually be equal net force times d. Well, if I multiply all of this times d, that d is going to be gone. And what I'm going to be left with, essentially, is m times Vf squared minus Vi squared all over 2. The reason I'm showing you this is because this is actually, that is K final, kinetic energy final, 1/2 mv squared minus K initial. And that is your net work. This is why it equals a change in kinetic energy. Okay, it's why it equals a change in kinetic energy. The net work does equal that. What this means is if something ever does a total amount of work on it, it will change the kinetic energy of an object. Now, you can get into scenarios here where, well, wait a minute, what if I'm lifting an object up at a constant velocity? Okay, so in other words, this is moving up at a constant velocity, okay, some mass. Well, I'm not changing the kinetic energy of it. Why is that? Well, if I think about it, if I pull down, what's pulling down on this is going to be force of gravity. I'm going to apply force applied. Now, if it's moving at a constant velocity, you will notice that this force and this force have to be equal because it's not accelerating. In which case, while this will do positive work as I move it up, this will do negative work at the same time. And the net work will be, you guessed it, 0. Which means there can't be a change in kinetic energy. Only when I change kinetic energy am I doing net work on an object. The last thing I want to talk about was conservative forces. Just a quick mention of this. Friction's your big one, and that if I go up, let's see here, if I have a big mountain here, okay, and I am sliding, I'm sliding some book up this mountain. It could be a smooth mountain, it could not be, but there's some friction on it. So if I take this path and I, go like this and wind it all the way up to the top, or I take that book, okay, alternatively, take a book from here, same height, and just go straight up to the top. I could take those two paths. Well, gravity is what's called a conservative force. It makes no difference which direction I move this thing. Okay, it makes no difference. It's independent of the path. Okay, in other words, if I move this up here or I take this, gravity will do the exact same amount of work no matter what. It makes no difference. But friction will certainly take away a lot more energy from this object going up this way than this way. In other words, friction is path dependent. It is what's called a non-conservative force. Okay, friction would definitely take away more energy from the object if it took a longer path than this one. So in order to minimize the amount of energy loss, I'd probably want to choose this if it's possible. Okay, but just to keep in mind some ideas of conservative forces.